Thank you, thank you. Yeah, I will be like a DJ. I need my, mixing machines and everything. The title of the talk is too long, so we will shorten it today because 40 minutes is not enough to go to dynamics. We will just stay with supervised and self-supervised structural data. My eyes are larger, like my mouth is smaller than what I'm trying to chew, so I overpromised a little bit. But what we will talk about today, and it still will be a tour de force, I promise. And thanks for the previous speaker, Paul and Jane. They have already gave you a tour or an architecture of deep learning. It was an overview of everything, and I got lost because it's like Baroque style, like it's everything and everything. And I don't understand things if I don't understand the bricks. So my lecture today is about the bricks. If I don't understand how the bricks are built, then I'm like, oh, this is just Lego, people just building those architectures. Then I feel a little calmer. Otherwise, it's an anxiety. How can you possibly understand all of those methods? They all look very different, right? But they're not. And so, well, let's dive into one single topic today. We will talk about, well, I will be repetitive. I will repeat some of the topics that previous two talks have covered. But those of you who are learning, for whom this is all new, you will see, if you see the same topic being repeated 3 times, that must be important. If you don't know about it, read about it. If it's not being repeated, maybe you shouldn't even look at it. So short biased history from me, then we will go into building blocks of CNNs. I want you to understand the CNNs as it's an educational course. And then we'll talk about predictive model based on those principles, semantic segmentation, and we will need more blocks for that. Then I will introduce UNet. UNet is now just a tool, just a Lego block, but we will try to understand what it's built of and how it works. And then I'll introduce another model that is from my group that is as good and powerful as UNet, but nobody knows about it because UNet is so popular. But it's about 1,000 times smaller. So then we'll talk about self-supervised or synthetic data training, how to address the robustness of the models when you don't have enough data, and I will claim that you need no data at all. So structural data looks like that. This is a T1 image, but we could have a T2 or any other image, which is voxels that you can display maybe in 3D, but this is our cube, this is our input data. That's it, 1 cube, 1 sample, not many cubes as in fMRI, not anything else. This is what we will be talking about and working with. And this is my bold statement. Convolutional neural networks work great for this type of data, and that's all we need right now. Well, maybe I can reinforce it just to make it controversial. For those who wants to work with transformers on that, yes, do that because it's popular and probably easy to publish, but it doesn't mean they will be better. Okay, so brief history, and biased, of course. Just 3 slides. 1962, David Hubel and Thorsten Wiesel tortured a cat and figured out how the brain, how the visual system of a cat looks like. Layers and feature detectors or receptive fields. That inspired many people, including Kunihiko Fukushima in 1979, who coded up this infrastructure that is practically a copy of the cat's brain from the original paper, but coded up. It's called neurocognitron. 1979. Well, actually, backpropagation already existed, and it was called algorithmic differentiation, AD, because it was invented in the 70s, in 1970, but he didn't know about it, so he didn't train it with backpropagation. In 1989, time delay neural network was introduced. We know exactly the same or very similar architecture by a name 1D convolution. But there was no name like that. It was used for speech recognition and used the same principles, etc., etc. 1989, the same year, actually, Jan LeCun already was playing with MNIST data and CNNs. Receptive fields, we will talk about them later. Feed-forward network at the output and prediction of the classes, which took him 10 years for, I don't know for what reason, but to make into this convolutional neural network that is LeNet 5, I think, that it's practically modular. Couple of modifications is what we're still using now. And one curious fact, this is an image, figure 2 from his paper, well, his and co-authors. Interestingly, it is about handwritten digit recognitions, but there is a letter A there on the picture, right? It's not a digit. Well, in fact, that's what they did. They figured out that when you train a network to recognize letters as well as digits, it performs better on recognizing digits. And right now, we have rediscovered it, and we call it multitask learning. Lots of models. I forgot their names because I'm not about architecture. I'm about the bricks. So I will tell you about the bricks. Okay, building blocks, the bricks. How do we get there? How do we build the network? So to build convolutional neural networks, we need convolutions. We need max pooling that didn't exist before, and we need skip connections. Convolutions are filters or feature maps or inner product, tied weights. Basically, you have, oh, wait, something disappeared. Ooh, sorry. Can we refresh? I don't think. Math is not showing, so I don't know. I apologize. Well, I had this little filtered math JAXT here, but it's not displaying for some reason. So what happens with this shaded area, each corresponding blue element gets multiplied to these little numbers that I had conveniently displayed here, but we don't see them now, gets multiplied and added. And so that's one representation. Another one representation is like that, and this is practically a convolution. Little inner product of 9 vector by a 9 vector gives you one number as an output. And to scan this 5 by 5 blue image with a 3 by 3 filter to get a 3 by 3 output, you have to perform those 9 operations, and you are done. But then what didn't exist, at least in LeCun's paper, is max pooling. Usually, we don't have to, as we will see in this presentation, but usually we want to compress representations or the outputs of neural networks. So when an input volume, in our case, goes in, and the input volume is 56 voxels on the size, you want to make it smaller and smaller in sequence. And the one way to do it is max pooling. You are looking at a neighborhood of pixels in this 2D example, and you're just selecting the max pixel that will go next. And in the differential programming style, everything works out. You can still differentiate, even though it feels like it's a discrete operation, but it doesn't matter. It's like an if then else. We can still differentiate through that computational graph. And this is an example of max pooling unfolded. But then what happens in 3D? All those beautiful animations are, of course, not mine, and I cited them. By the way, if you want access to the slides so you can feel yourself as a DJ, as I do myself right now, go at tinyurl.com, capital OHBM 2024, and you will have my slides so you can play with them and you can see all the links, you can click through them. So in 3D, what we do, we take the input volume, usually 256 voxels on the side, And we scan by 3D 27-element filters, 3 voxels on the side. So we convolved, or for those of you from signal processing background, it's basically a matching filter, not a real convolution, but we convolve with this feature map and create another output. Padding is involved because we, in this figure, we want the same size input to create the same size output. For each voxel in the input, there will be a voxel in the output. But one input volume in this situation will give only one output volume. So we use multiple filters. The same filter, parameter tied, is convolved with the volume, and then another filter with other parameters, which are trainable. That's what we are training, those parameters. And compared to the size of the image, input image, the parameters size is tiny. So convolutional neural networks are very economical in their parameters compared to many other models. But then we have multiple channels. Two as good as an example of multiple, right? But we can have 256 or 512 and up to whatever we want. But so imagine those are more than 2 channels. So what happens when we have multiple channels as an input? This multiple channel example also works for multimodal inputs information, because as you have inputted T1 here, you can add a T2 or flare or valve or whatever. You can just add multiple inputs like that because you can work with them as separate channels. When you have multiple channels, that means multiple cubes in our MRI case, what happens is there are multiple filters, but they are tied to the same voxel in the corresponding channels, and they all create one single output, one voxel, by multiplying the parameters with corresponding input values and then just summing up. So think about it as an inner product with corresponding inputs. And the same for another one. So you're stitching across all of the channels or all of the input volumes when you are convolving. Skip connections, very important concept. And I think misunderstood, or at least it's misrepresented, maybe for a reason, and you see a reason. So highway networks. Highway networks appear on arXiv in May 2012. They are officially Neural Information Processing Systems Conference 2015, December presentation. But on arXiv, they were on in May. May is the deadline when people submit to this conference. So they submitted and put it on arXiv. Oh. Yes, that's what happens. Why is it not rendering my math? Oh, my apologies. This will be, but this is like the only slide where I need math. Is there a Chrome? Oh, okay, perfect. Okay, let's keep our fingers crossed. So this is one layer of any neural network. This is I'm a little bit sidetracking, but usually we represent layers as functions, and we think of a function as something that takes input X. But in fact, because we're training a neural network, this function takes 2 inputs. The parameters are also an input to this function. So my parameters are W, and my input is X, and Y is my W. Of my output. Why is my output? So, okay, it's a little bit strange representation when input and parameters are grouped together to this function H. But this is any layer of a neural network can be represented like that, parameter and the data. So what they did is they said, instead of just doing that, let's expand it a little bit. So let's take our original layer and multiply it by element-wise, which this is also another important concept called gating. It's a gate because we have a sigmoid nonlinearity in T. T is for transfer. So transfer also takes the input, has its own parameters, and decides whether to open or close the gates, because sigmoid can be saturated to 1 or to 0. If it's at 0, then the specific value of y doesn't matter, or this function doesn't contribute to this value of y. While this x, the original input, has a side path into the output, side track, and they introduced this carry gate. Gate because, again, sigmoid. Too complicated already, right? So they simplified it. Well, so they thought. They simplified it with one transfer function that decides whether the gate is open. That means the layer then, whatever the layer has computed, will be the output. If the gate is closed, then there will be a 0 here, and the previous value not affected by this layer will pass through. Everything is trainable. So what is happening, if the transfer gate is closed, 0, then no modification to the input is happening. It's just passing through to the output. If it's, again, if it's open, then we're modifying. However, in this paper, they correctly recognized that this modification is done for one and only one reason. In order for the gradients to flow back when they can be vanished inside of the layer. Inside of the layer, the gradient on the reverse mode AD can vanish. But this path through X will always allow us to train. Even if the gradients vanish here in H, in our layer, we can always train the layer before it anyways. So that was it. Looked too complicated, but was powerful as demonstrated. Without, let's take a deep neural network and start increasing the layers from 10 layers, 20, 50, 100. And those are epochs, and this is finally displayed in a mirror way. So let's just look at this picture. This is our loss function cross entropy. So the lower, the better. But as you see, as we increase the layer, the number of layers, cross entropy goes up. It becomes worse and worse. In their case, in highway networks, it doesn't go up as much, just a little bit. And this is higher, the better, training entropy error. No, actually, higher is worse as well. So, okay, it worked beautifully, but at the same time, in December 2015, another paper appears on arXiv, and this paper says, okay, let's just forget about this transfer gate. Nobody understands the gates anyways. Let's just have X be added directly to this function. This F is just the H output, and this is a residual connection. Okay, this paper confused everyone because they had this story about residual, blah, blah, blah. Don't believe that this is all done just for training. It improved the training dramatically. I will show you a visual demonstration of that. So now the gradient, when you optimize, if the gradient that's supposed to flow back here, the gradient computation, would disappear here because of tiny numbers sequentially multiplied by one another, this gradient will still be able to flow back. That's the only reason. What happened is we were able now to train. This is ResNet. Everyone knows about it or heard about it, but all that there is a skip connection. Skip connection is the main building block in the architecture. Next time when you see this intricate construction, look for skip connections. Are they there or not? Because then you will understand how it's trained, or whether it's trained thanks to those skip connections. So how they work? Let me skip that just for the interest of time. It did improve things a lot. Just trust me on that. But in 2018 at NeurIPS, again, the same conference, people figured out how complex billion-dimensional error surfaces can be displayed in 2D. So this is without a CNN without skip connections, and it's looking for this minimum. When you add skip connections to the same network, look what happens to your optimization landscape, to your error function. It becomes much smoother. That's the effect of skip connections. And already a function or a model that Paul has mentioned is DenseNet. Here's a dense net, is where skip connections are all you need, kind of, before, you know, the self-attention, all you need. Add skip connections to everything. Look what happens to the same thing. It just almost becomes convex. So much easier to optimize, much easier to find the minimum. So, okay, now you know everything you need to build those networks. You have skip connections, you have max pooling, and you have convolutions. Max pooling allows you to reduce the size of the input activations. So you start with a large input. I say 3D, but I draw 2D. Sorry about that. Just imagine it's a cube. This is a network from deep residual learning for neuroimaging application to predict progression to Alzheimer's disease. And it's just a classification model, but it works on structural data, and it works quite well. It works, this is that specific paper. The more layers you add, not too many layers, not just layer 1, layer 2, layer 3, and with 3 layers, you're already kind of overfitting, but still performing well on validation and on test. This is a property of the entire deep learning, hasn't been mentioned yet today. They're overconfident, they do overfit on training data, and yet they do not, they tend to memorize the training data if we judge by the classical statistical approaches. But on validation, on training, on test, they still perform quite well. But they're also overconfident in their scores. They think they're right when they're not. But that's another story. And this is another paper. We showed there, well, actually, the first author, Anis, that when you have a lot of data in neuroimaging, as well, and it's a known result in anywhere else but neuroimaging, I guess, that the more data you have, the better is the accuracy, the better for deep learning networks, not for the classical algorithm. Deep learning networks, accuracy benefits from the size of the data as it grows. So that's what is shown here. Let's keep that. And switch gears to segmentation problem. In segmentation problem, especially in semantic segmentation, this is from Free Surfer, a classical approach. I think runs for 8 hours now. I remember the times when it runs for 32 hours for one subject. You have to take a brain, an MRI, and segment into an atlas that is semantic functional atlas that is not just gray matter and white matter. So besides what we just learned, we are missing one convolution to build the next model. We're missing understanding what a fully convolutional network is and up convolution aberration. So one convolution is just like that. There is just one number that gets multiplied to a pixel in this image, and you get the result. Seems funny and useless in this animation. But imagine you have multiple channels, because when you have multiple channels, what it means is you're collapsing all of the channels in a weighted, learnable manner into a single cube or a single channel. That's what it's for. That's the only reason, to collapse all of the channels in a learnable manner. That is one voxel, one voxel. Each one is multiplied by some parameter. If you are good in visual linear algebra transformations, you can recognize that this tensor is multiplied by a vector. It's an inner product with a vector in the 4th dimension of that tensor. You're just collapsing it that way. Now, what we can do, this is a classical classification problem. You have an image of a cat, you have multiple convolutional operations, and then you apply fully connected layer down to classes, number of classes. The caveat and the catch is that convolution is shift invariant. I mean, that's what it was created for. So your input can have any size for the same convolutional network. It doesn't matter. You don't need to retrain a network for the size of the input. The input can change. Even if you trained on one size, your input can change. But this fully connected network spoils the fun completely, because it specifies the size exactly. And so everyone, all of the libraries that you're using, they're cropping and kind of pushing the size of the input to a specific size. But if you only have convolutions all the way from the start to the end, you can train on one size, use it on multiple sizes. Convolutional neural network, fully convolutional neural network, doesn't mind. But the key is, for us, is that we get an image, and we get an image of the same size as an output. Any size input image will generate the same size input image, output image, sorry. So that is fully convolutional neural network, a useful concept. And another concept that is a little confusing, but the animation is more helpful, I think, that at least in the talk. When you're alone at home, look at this. This is a beautiful Stack Overflow picture some Good Samaritan drew by hand for us. It does convey how it works, but basically what it is, you have 9 parameters that are all scaled by one input value, and you up projecting, you expanding your smaller image to a larger image. Now we have all of the blocks to build our first fully convolutional model, 2014. Input image gets sequentially successively contracted and then expanded with up convolution back again to the original size, and you can now you have a model that is insensitive to input size, can take any input size and can be trained on any input size. But we need one more concept. We need the concept of encoder-decoder. Autoencoder has been mentioned by multiple times in both of the previous talks. But I need this autoencoder for abstraction because almost all of the neural networks, I argue, maybe all, can be represented as encoder-decoder type. Even when they tell you, oh, it's decoder-only transformer or encoder-only transformer, you can still find a bottleneck in this model where there is a previous number of layers that encode into representation. That's this part. And then there is another model that decodes it. So we will need that distinction, that encoder encodes into some lower dimensional, smoother space, and decoder decodes back from this lower dimensional, smoother space. Smoother is just because we're training it by stochastic gradient descent with differential programming. It will have to be smooth, but lower dimensional because, again, because we just coded up to be so. So we're ready to put together up convolution, fully convolutional, encoder-decoder, and skip connections. Meet one U-shaped neural network that uses convolutions here. Imagine this is your MRI image, 3D. You apply convolution and max pooling here. Well, in this particular image, we're using larger stride instead of max pooling. Then you successively contract the size of the input until this bottleneck layer. And this arm of the model is our encoder. And then you apply up convolution. Ignore the red skip connections for now. I will come back to it. Apply up convolution successively to get the same size output. This is just an autoencoder. We start from the larger brain, then reduce the dimensionality with a number of successive convolutions followed by max pooling. And then we again up convolve, that is expand dimensionality, just autoencoder. Only we didn't train it with reconstruction error, we trained it with segmentation at the output and MRIs at the input. Doesn't work, very hard to train. You know why, right? Because the landscape is not smooth. So we need to add skip connections here. The way UNet, that's the name of the model, by the way, if you didn't recognize it yet, although the shape is V because we like to rebrand. Somebody published the same year. Thankfully, they cited the original UNet paper by Olaf Ronenberger and called it, okay, because we're using it at 3D data, we call it VNet. But the idea is the same. So you have skip connections here from layers with the same size images. And the motivation in the paper is, in his paper, the original paper, is that by doing the autoencoder thing, autoencoder path right here, we're losing high-dimensional information. So we're backfilling this high-dimensional information. The lower the spatial information, the smaller the more high frequency, sorry, not high dimensional, high frequency information you lose. So you backfilling this high frequency information with. Well, UNet took over the world, that's a fact. It's hard to argue, 86,000 citations, but it's practically, I mean, people are generous, they're citing UNet still, that's why 60,000 citations. Nobody cites MLP, right? We just write, oh, multi-layer perceptron. So UNet became a household name. It's just a tool, it's just a Lego block, it's a brick that everyone is using, but it is so useful and so powerful. It works for multiple things, which I will show. But there is a problem. There is a problem with UNet is parameters and memory usage. So consider a small UNet. It's a very small UNet. It just has 5 layers, 1, 2, 3, 4, 5, of down convolution and contraction and up convolution. So this small UNet already has 23.5 million parameters. So 23.5 million parameters maybe doesn't feel a lot until you are in distributed settings where you have centers around the world and you have to exchange the parameters while you're training the model and you know, things like that. But there is another problem, and another problem is, and I don't know if this is my statement or it's a common sense, but skip connections are bad for memory. If we start here and we generate large number of activations, large number of channels, we have to keep them in memory until the entire computation is over. And we accumulate this memory at each layer. We accumulate, even at inference, we're not doing any training. We need a lot of memory, a lot of RAM. And well, why should I care, right? At my center, I have a lot of GPUs with 80 gigs memory, and I assume all of you do, right? Because you're here, you're listening about those deep learning models, I assume you can run them. But, well, actually, I do care. And one of the tricks that people were using all the time was, well, why should we train on the entire brains? Let's just chunk the brains into little cubes, train on subcubes. I just told you, you can train on smaller things and apply to larger things, right? But even application is painful because of the memory. And then we can do ensemble. Fine, it worked fine. People have done that, but then, until we realized that full volume training is better. We're getting more accuracy, higher dice score, etc., etc. But it requires 80 GB cards to train batch size of 1. Only 1 input can be used at a time. And other problems that I will show later. Why would we care about this, right? And I think, as one of my students said, we Stockholm ourselves into the current situation and we just don't understand what we're going through. We're talking about all these multiple models. The previous 2 talks, including my talks, mentioned multiple models. But how can any sane person, maybe not people in this room, but imagine a clinician, use any of this model? There is a 0 chance of them going, installing Conda, CUDA, all that jazz, like lots of versions. But go to any of this model. Yeah, some people share the source code. You know, this is nice, very nice. Not all people share the source code. But when you read the README, it's like, oh, go through this trouble and then use that model. And it's considered easy to use. Well, slightly there is container usage. Okay, this model is containerized, so you pull a Docker container from Docker Hub. There is that. Or give us our data to our cloud. We promise we're not going to do it, and just trust me. Well, anyways, sorry. But there is another way. There is another way that I advocate here. It's edge-based deployment, the browser. All my slides are in browser for the last 10 years, and I'm going through the trouble every time, I guess, now when I'm trying to present at a conference like that, but I get my DJ set, you know, for free in return. And so why don't we put all of our models into the browser so people can click on a link and get the models so they can use them? Well, 23 million parameters and 80 gigs or 12 gigs, not every browser can support. But we need one more block, one more brick. You have many bricks today. tinyurl.com, OHBM 2024, so you can refresh on your bricks after I'm done talking. This is called dilated convolutions. Number of parameters is still 9, but I'm introducing the gaps between those parameters. Just to translate that in 3D, we're doing it in 3D. So when I'm introducing the gaps, I'm covering larger area, larger receptive fields with fewer layers. For a dense 3x3 filter, I'm adding only 2 pixels at the margin, or one pixel at the margin with each layer. So in order for my top layer to see entire input, I have to go too far. With gaps, and the gap doesn't have to be just 1 like here. It can be 16 or anything. You can quickly expand, telescopically expand without going too deep in the layers. And then, this is UNet building blocks, right? Up convolution, fully convolutional neural networks, encoder-decoder architecture, and skip connection. Let's throw this away. Let's throw this away. Let's throw this away too. We will need fully convolutional neural network. We are doing segmentation still. And replace it with dilated convolution. Well, it's not UNet anymore, but fewer better, because the fewer things you have, better luck of trying to put it in a smaller form factor. So this is MeshNet. It's an isometric model. Size doesn't change at all. There is no encoder-decoder. Your input and next layer, each layer has exactly the same size, and it goes in feed-forward manner. So when you computed the layer 1, you don't need the memory of that layer anymore. Throw it away. Free the memory, compute the next layer. So you're using the memory just for 1 layer. And for 21 channels in each layer, you're using only 72,000 parameters. So compare 72,000 to 23 million, about 300, I think. But you can go lower. This is for 21 channels, so you can go for 5 channels, and it's even smaller. Trust me, performance is comparable. No magic. We cannot beat UNet. We cannot beat millions and billions of parameters. They're still better. Like, keep adding parameters in those cards, GPU cards. But look what we can achieve. Some simple model. This is running right now on this laptop, and it loaded as I opened the site. The model is in the laptop, and okay, we run this brain extraction model. I have many other models, but no time. I have tissue segmentation model. It's also brainchop.org. Go there on your phone. Well, it will not work. It will open on the phone, but the deep learning models probably won't work because you don't have, your phone is cheap, sorry. Yeah, iPad will run them. iPad will run them, and if you have a pen, you can edit the output if you don't like. So one thing is you can save the results. Another thing, you can save the entire scenery. Email it to your clinician friend. Tell them, go to brainchop.org, drag and drop what I emailed you, and you will see what I saw. And tell me, is this a lesion or not, because I'm looking at it. I have this problem all the time, because you send a nifty file to a clinician, and they're like, what is that? Can I look at a video? Or and I've done that. I've done a YouTube video for them, and that's a pain. With this now, it finally, hopefully, becomes portable so that real people, not just 300 people in this room, can use those tools. Fingers crossed. But tiny models, no magic, are less robust. Tiny models are harder to train. Well, we figured out how to train them fast. But how to train robust models, how to do something with the data so we can train robust models without requiring all the data in the world. And we can generate the data, as you've heard in previous talks, right? But surprisingly, this generator doesn't require Paul Thompson coming out with his talk and talking to us about this very, very complicated model. These people from Eugenio Iglesias at MGH figured out that Gaussian mixture model is all you need. Take labels from some real people. Throw away the data. Just labels from FreeSurfer, generated by FreeSurfer, or human labelers if you're lucky and somebody donated you a week of their time. But take those labels, then modify them, squish them, do something to the labels, run your Gaussian mixture model, GMM sampling from those labels, add some deformations, and you're done. This is your training input, this ground truth data. No real data is involved at all. On this synthetic data, you can train a model that is very robust. It can run on clinical data. It can run on babies' brains, for those of you who've tried a very, very difficult problem. And can do many things. It doesn't show all of the, I do have citations to the corresponding papers and projects on tiny URL, trust me. When you go. So synthetic segmentation. No real data is used besides the labels. 300,000 images, all synthetics, were used to train this model, and it's very good if you haven't tried it. But you know, you have to go through the pain of Conda and all of that. Yeah. So synstrip can extract the brain from many, many, many modalities. It's not sensitive, it works really well. Also trained in that manner. Synth SR, super resolution, that was here today already. Also trained only on synthetic data. And I call it self-supervised learning because we're using one only principle in the entire deep learning is, well, we call it backpropagation, but it's reverse mode AD. It's differentiable programming. We're still training with some ground truth signal. It's only the ground truth signal here is fake, or, well, it's generated. The catch, training takes a week. That's why SynthSeg paper, which introduced augmentation model or synthetic data generation, the model is called SynthSeg because there is only one model that they care to train. It's very hard, right? You're training 1 week and you're changing another hyperparameter for another week because the way they train it on one single large GPU, one sample at a time. They first generate it, before that they train GMM, so it takes seconds. In the world where everything takes nanoseconds, things that take seconds drop your GPU utilization considerably and you go very, very slowly. I can't stand that, sorry. So let's decouple. This is a differential, mechanical differential. I thought this is the simplest way for me to explain to you what I'm going to tell you about now. Is like in your car, you can turn on curves so that one wheel is rotating slower than the other and nothing breaks apart. So let's just decouple, well, because the real thing is much more complicated, right? What we've done, differential is very easy compared to what we have actually done, but we took the generator from this synth family. Thanks for them for publishing their code. Fantastic. If you're thinking or not to publish your code, please do. Everyone will benefit from that, from your code available. And from 7 days a week training, we can train models other than UNet. We train the MeshNet model using their approach in just a night. And a night is reasonable, right? You can experiment now. You can run one architecture and another architecture. And, okay. It'll take longer. It's a larger model. It is robust. It can work on clinical data. By the way, brainchop.org, drag and drop your clinical image, Nifty image, or MGZ, or any other 10 formats that we support. Everything is local. Nothing is sent. There is no backend. Everything is running in your browser. Done. So this segmentation is done right there in your browser on this 256 by 256 brain, and you have here the display of the structure. etc., etc. Oh, I don't know how I'm doing on time. Am I done? Stop. No, okay. No. I didn't hear that. So what okay, I'm concluding actually. So what we have learned, how volumetric CNNs are built. So you now are not scared, right? I hope to reduce the fear in you. And then UNet, very good model still, even though it's a dinosaur, but it's large, but it's very good. And then how to simplify this model and build smaller models that are as powerful, and how to efficiently utilize self-supervised or synthetic data training, and how to use segmentation models anywhere with zero footprint. No installation is required of anything. Okay. Thank you.